Yeah. All right, let's get started. That's better. Okay, so today we'll continue the discussion on peer-to-peer networks. Last time we were kind of starting out with a little bit of history. I guess you could say that peer-to-peer networks, in a sense, they're all kind of history. There isn't that much peer-to-peer networking going on. I'm not sure that has to be like that's sort of the end of it. I think there's still plenty of promise for it, and maybe one of you folks will bring it back into the limelight. When where we left off was the Nutella protocol, or the Nutella protocol. The problems with the Nutella protocol, well, I guess the main problem it had was legal liability, because it was used mostly for illegitimate purposes. But there were a couple other problems too. There was, let's say, the centralization of, legal liability, and then there was the scalability of queries. Right. So to find a file that you want to download with the Nutella protocol, you have to send a query to some of your neighbors, some of your peers. Right? The network as a whole may have tons, hundreds of thousands of members in this peer-to-peer network, but you wouldn't know who those hundreds of thousands of members are. You would just have connections, or TCP connections, links really to a handful of other nodes, and that's it. So in order to find some node that has the file you want, you would send a query to the neighbors that you have, and they would forward the query to their neighbors, and so on, a number of steps, until at some point someone has the file that you want, or a file that sort of matches your query. At that point they would respond directly to you, so that you can contact them directly for a download. Okay, so the scalability of queries, the problem there is you're sending a whole lot of query packets around. You're doing this kind of undirected search throughout the network. You could imagine, if you don't have a time to live sort of expiry date on the query, that it would actually reach the entire network. So now you have 10,000 nodes, 100,000 nodes processing your queries, which in turn means that you would be processing the queries for 100,000 nodes, right? Because everyone here is a peer, they're all doing essentially the same thing. So for this to work, you would have to pour in tons of resources. You would have to have lots of peers who do nothing other than just provide query support and uploading files for you. So scalability of queries, right? Its cost is quadratic, or total, let's see. Quadratic number of nodes. So basically, the network gets slower and slower as you add more nodes onto it. And you would want it to be the other way around, really. As you have more users, you want it to go faster, or at least stay the same. Okay, and another problem, perhaps, is the downloads, sort of primitive download facilities. And in particular, there is no incentive mechanism. So the problem here is you have people who nicely share their files, and then you have lots of leechers, freeloaders, who will just query a lot and then find files they want to download a lot, and then basically close the application down after they got what they wanted. So this takes a further load on the network. Now you have these. Usually the principle is, as the network grows, you have more resources because there's more users, and you have more queries, sort of matching the amount of resources, so you would get a nice stable performance. But if all the users are users that just came on the network to try to get something they want and then get off, then more users doesn't translate to more resources, it just translates to more work. So this was addressed in 2 different ways. Well, let's see, actually. There's 3 different problems here. Legal liability, this being, anyone can figure out that I'm hosting these files that I really shouldn't be hosting, and therefore go after me. And I keep using the copyright as sort of the law-breaking activity that we're undertaking. But there's plenty of similarly law-breaking but more legit activities too. Like you might be posting a treatise on the current political system. And here that's okay. In fact, nobody reads it. But if you do it in other countries, you might get executed. And so there ought to be a way to distribute literature to your peers without getting caught. And here, usually the literature is the latest Marvel movie. In other places, it could be something of more importance. So I don't think that it's necessarily a good idea to be copying these very expensive to make crappy movies. But it sort of serves as a good practice ground for more important pursuits. Okay, so the legal liabilities one. Need to somehow hide who's doing the stuff, like who is uploading this illegitimate material. And then, or at least maybe share liability. So if you're getting some, you should also be in trouble, right? So you kind of share this problem. Scalability of queries, it really needs to be much more efficient than growing quadratically in the number of nodes, or it's probably even worse than that because there's loops and things in this weird network. And then for the download, we really want to incentivize users to provide lots of upload while they are downloading, so that the total capacity of the network grows at the rate as it grows, as the number of users grows. Okay, so let's look at a solution that addresses these 2, scalability of queries and primitive download facilities. This one's called BitTorrent. It's a pretty interesting design. Basically, they said, forget about the queries. Who cares about the queries? Just let's just figure the download out. So with the BitTorrent, every media file, everything that you want to download. This could be a movie, but it could also be a Ubuntu DVD, or it could be a book, or whatever you want. Is identified and somehow described by a .torrent file. So this torrent file has a few important pieces to it. It lists one or more trackers. A tracker is a computer that knows others who have this file. It's really called a swarm. So there's a swarm of BitTorrent clients are computers who are currently interested in this file. They may have the whole file, or they may have just pieces of the file, but they are interested in collaborating on downloading this file. Maybe we should identify a seed in particular is a machine client that has the entire file. It's not really that important of a distinction, but you could imagine if there's only one client who is interested in this file so far, and in comes another client who has nothing of the file, then the first client who is interested in the file, they would have to have the whole file, or together they can't put together the whole file, right? You need someone who has everything, and that's a seed. So as soon as you've downloaded everything you need for this file, you're a seed as well. And the other ones I forget if there's a name for them, but they're a BitTorrent client as well. Okay, there's something more in here. There's also some hash signatures for file, what are they called? I think they may be called parts. So this describes like, oh, what should the contents of this file be? So you could imagine you compute a hash for the whole file. If you're not familiar with content hashes, it works something like this. See if I have an interesting file on my desktop, maybe. Okay, we'll take this one. It's a screenshot. Oh, we'll take this one instead. No spaces. So here's one way to compute a sum. Oh, I guess that's not how you do it. Maybe it's like this. Come on. What happened here? All right, so I have this file, and I run it through this program, and it computes a number. And this number depends on everything that's in the file, but that depends on every bit of the file, right? So it could, for example, be, you can imagine this is a large integer. You could just XOR the entire file, every chunk of this of the file together, XOR it all, and you would end up with a hash like this. Lots of different ways to compute hashes. BitTorrent hashes are extra cool. I think we can skip that. They're a sort of a hierarchical hash, if I remember correctly. In any case, the torrent file says that, oh yeah, the first 10%, 1% of the file should have this hash. So if you downloaded the whole thing, you might not know. As a BitTorrent client, you don't really know that you got the right stuff. But with this hash, you can actually verify that. Oh yeah, I have the first 10%, right? And it actually goes more fine-grained than that. Okay, it has an incentive mechanism, which is really nice. You get faster download from me if I get something from you, right? So every client is programmed to give a certain rate of upload to every other peer they're talking to. But they prioritize those peers who send them something in return. Of course, yeah?
When you say something in return, is it the same thing you're downloading and whatever?
Yeah, that wouldn't work, unfortunately.
Okay.
So you split the file into lots of parts.
Yeah.
And I send you the first part, you send me the 100th part.
Okay.
Right? So we keep exchanging like this. And as long as you have something new that I haven't seen before, that's valuable to me. So I would ask you, like, what parts do you have? And you say, okay, I have these. So then I ask for one of those parts I don't have. What's really nice about this is it also gets every client to pick the rarest part. But I'm kind of getting ahead of myself a little bit. We haven't talked about exactly how it works. Maybe we'll do a little drawing. No, screw it. Why don't we just go to the website? Let's see. Pirate Bay. Let's see if they're up. What is this? ThePirateBay.org. Okay, cool. Just so I don't get in trouble, let's go for Ubuntu. Okay, so that's the one we want. And here we say get this torrent. And so you see, this is all a website, right? There's nothing peer-to-peer about this. But now I told it I want to download this. Let's see, where did it go? Get this torrent. Oh, there's some magnet link bullshit. Does it have to be like that? Let's see. Oh. No, that's not good. Okay, anyone have any other suggestion for a torrent site?
You got a Linux distribution site. I'm pretty sure they distribute it.
Okay, we can try that. It's not as fun, but Lime torrent. Oh, okay. Yeah, I was trying this with this one. Okay, this will work. Because I tried this before at some point. All right, so I hit this one. Here it says use a VPN. We'll talk about what VPNs are some other time. Come on, get it. Another magnet thing? What? Come on. Okay, I think I actually downloaded this sometime before. Let's see. I don't understand what the problem is now. These magnet links, they are a way to open up another application, in this case a BitTorrent client, right? So that the BitTorrent client can connect. Right. Okay. So here's the file that I was hoping to download. Okay. All right, so here it is. All right. So it says, okay, these are some trackers. These are some servers that know about this file. So if you want to start downloading this file, contact one of these guys. And there's lots of them. It's not a lot of work to be a tracker, so a lot of people contribute. And then it says, oh, there's, every piece is this long, there's this many pieces, and then comes a bunch of hashes that say what the pieces should look like. So once you've downloaded an entire piece, you can verify that the guy on the other side wasn't lying. You actually got the piece that you wanted. So this is a really important part for the incentive mechanism. All right, but I wanted to see what this looks like. It's quite similar to this one, but now we have a tracker. And then we have a swarm of these BitTorrent clients. But in this case, it's an interesting swarm because all of these, they want the same file. Right. So all of these are known to the tracker. Here comes me, and I contact the tracker. I get a list of BitTorrent nodes, clients, who are interested in this particular file. So now it's a much smaller network than it used to be. There's no real coordination between BitTorrent users overall. It's just the people who want to download Ubuntu 18.04. That's it. Okay, so I contact a whole bunch of these peers, and I say, I'm sorry, I have nothing. All right? So some of these may be seeds. They may have everything. Some of the other ones are I think they're called leechers. But a leecher ought to be one who doesn't have anything, so I'm not sure. I'm certainly a leecher at this point, right? Maybe they're just straight up peers, the ones who are cooperating properly. Okay, so I get a slow connection. Now I'm talking to these three seeds, let's say, or two seeds, maybe one normal guy, and I selected two pieces of this file. So I slowly download those. And now finally, I have a couple of pieces that these other guys don't have. This one doesn't have it. This one doesn't have it. So now I can ask these two for two new pieces, and they're going to come slower. They might say, no, you're cut off. I already gave you two pieces. Forget it. Because they're seeds. They can do whatever they want. They don't need anything. They're just there to help. These other guys, they really want the pieces that I have. Right? I on purpose got pieces that they don't have, so that I can trade with them. So now I get one of his pieces, ideally something that this one doesn't have. Right? So I'm switching that for one of the ones I have, and now suddenly I have three pieces, and then I switch over here for another one, I have four pieces, and maybe I can trade the ones that they got from between each other, and so on. Right? So over time I build up a larger collection of pieces of the file. Eventually I have all the pieces. Sometimes with the help of the seeds a little bit more, sometimes by having to connect to some more. Every now and then, these clients disappear. How does a client disappear? Well, they close the lid on their laptop, right? Now they're off, because these are all just regular dudes sharing files. So it's not that you can trust any of these to stick around or to even give you the proper stuff. Like it's in their interest to lie. So you have to verify. And that's the other piece there with the torrent file. It says the first piece should look like this. So you get that first piece from one of your peers, and then you know that you can trust them. And then you can up their bandwidth rate and so on. Okay, so we have a nice incentive mechanism. We have a way to prove or to verify content. It's nicely scalable. There's no query mechanism at all. Right? Yeah?
Are the pieces compressed?
That all depends on the file. But usually any file you download from the internet will be compressed. Like
But
it'll be a
the
deemed.
protocol doesn't compress.
No, there's no point in doing that. Any file compression mechanism will be more efficient than a protocol compression because it can consider the whole file. It's cool stuff. If you want to learn about compression, probably take a class in ECE. They're the best at that sort of thing. Okay. Yeah.
How does this overcome the private IP source?
It doesn't. So here I am registering myself with a public computer saying, I am willing to share this file. And so now any trolling lawyer can go through a bunch of trackers looking for nodes. And not only that, they can ask to download a piece, right? And once they get that piece, they know that you have the real file and you're sharing it. There was a problem before the DMCA, the law that made all this possible. The copyright holders would hire sort of mercenaries to put out fake content. Right? So they would join Nutella or something, and they would like give you movies that say, "Oh, you shouldn't pirate movies," right? And that got annoying, so then people would use Nutella less. They would rather pay for it and not have to have all this trouble because it takes a long time to download a movie. Maybe you're even paying for the bandwidth, and then you get this crap, right? So at some point you get tired of it. That was the original approach, but then that got fixed with the torrents. Because the torrent says, even after you got just a little bit, you know if it's the right stuff. Okay, but yes, it doesn't do anything about liability. I guess it's a little bit like how they do in police dramas, like the police can't start the transaction, do something bad first, like that. You have to kind of solicit them for drugs or whatever. So similarly, you could refuse to be a seed and refuse to give anything to any peer unless they give you a legit piece first. And then that might be a little bit safer, but really it's kind of silly. Okay, but BitTorrent is really nice in this sense. It also, scales nicely with number of users. More bandwidth or more downloaders. So at some point, if you start out with just one and you join in, now you can just talk to one. That's actually not as good as if there's two peers already you join. Now you can talk to two peers. That's probably better. Right? But then at some point, if there's, say, 100 instead of 1,000, it doesn't make a difference to you. So it's just that now you connect to a different set of 10 than some other peer. Right? So you're kind of spreading the load over a larger network. That's really good. It doesn't make the performance better for the individual user. It just makes it, kind of keeps it constant. There's no extra cost for the network being large. You kind of rely maybe a little bit on people being lazy too. Like they start their application to get their file, and it takes forever, so they go and do something else, and the client keeps running, and at some point they become a seed. Now they don't cost anything for the rest of the network. They just provide resources to the network. So in that sense, there's some benefit to, I guess, applications being written not to shut down after you're done. And BitTorrent clients tend to be like that by default. Okay, can anyone see any problems ignoring the legal stuff with this thing? Yeah?
What if there's no seeders?
No seeders, yes, then it doesn't work. There has to be someone who has the whole file, or at least together everyone has to have the whole file. But that's true for any peer-to-peer network. In some cases, I remember seeing somewhere that, say Ubuntu, they would say, okay, here, we're hosting this file, we have a seed, right? And if you want to download it, we're going to give you full speed, that's fine. But then many users want to download it at the same time. So now that seed, their one computer is handing out pieces to millions of users who want Ubuntu right now. And then they're all kind of sharing between each other. So you get to scale up that one seed tremendously. And that's really nice. If no one actually wants to provide the file at all, then you're out of luck. Yeah?
Say there's 0 seed, but then one person starts seeding. How would the network know that that person has started seeding?
Yeah, so it says in the torrent file which are the trackers. So when you start seeding a file, you start up your client, you say, okay, I want to share this file. Then you would contact a bunch of those trackers and say, here it is. Right? I have the whole thing. So next time when someone wants to download that stuff, they would look in the torrent file, contact some trackers, and then they would know about you.
So are these trackers like fixed servers or can they?
Yeah, so like we said here, let's see. So here, looks like this. See, this is a server in Turkey. It's on a HTTP port. I guess most of them would be. This is some Greek pirate party thing. Here's a European thing. There's a ton of them. So you could contact all of them or some of them as you please.
If all those trackers got taken down, then the entire network would work.
Yes, absolutely. Well, no. If all of these trackers went down, this torrent file would no longer work.
But like in general.
If there were no trackers, then yes, you cannot use BitTorrent. Yeah. But I think that would also be the case for every peer-to-peer network. You need a rendezvous place, like some way to meet others, right? And this is one good way. Yeah.
So the tracker file itself contains the thing that allows you to check to see if the first bit is good, right?
Yeah. Not the first, like all the 100 pieces or whatever it says in here. Like there could be thousands of pieces. Right?
So I guess as far as problems go, what if the track file, torrent file you get is malicious, like bad?
Oh yeah, if the torrent file itself is no good, then you will download the wrong movie or the wrong file. Absolutely. So you still rely on someone providing you the right torrent file with the right hashes in it. That's absolutely right.
What if someone starts a tracker server that is pointing to that? I guess the file would.
You would pretty quickly end up not having any users. Right? If you go to this website and all you get is garbage, you're probably not going to use it. And so that brings us to another kind of weakness of BitTorrent. There's no search, right? So if you want something, you have to go to a website to get the torrent file. The website is really nice in that they don't need to have almost any bandwidth capacity, right? Because all people are doing is searching, like it's this one, you know? What is this? It's just a little bit of text. It's really cheap. You can host it anywhere, so that's awesome. For legitimate purposes, it's a really nice design. For illegitimate purposes, the problem is, like the piratebay.org, it often gets taken down by some legal authority or another. They keep moving around, but basically, whoever's providing the torrent files is seen as liable for the copyright violation. And the same would be true for any other violation, right? You're talking about the wrong political party. You could have a secret file, right, that anyone can download over BitTorrent, But the torrent file itself has to come from somewhere. And that somewhere is a problem here. Yeah.
I was just gonna ask, are the trackers and the website that distribute the torrent file technically violating the law?
I think so. Yeah.
Even though they're not actually distributing the actual file itself?
That's my understanding after the Digital Millennium Copyright Act. Yeah. But I'm not a legal scholar. Take the class with Bob Sloan. He teaches a class on this sort of thing every now and then. Yeah.
Can you go back to the file? So for anything that's not port 80, it seems to say just UDP in front of the tracker.
Mm-hmm.
And is that just generically, if it's not 80, it would use UDP?
I don't think so. So here you have 8080, for example, right?
Well, no, yeah, anything that's not 8080 or 80.
Yeah. So trackers, it makes sense to have trackers that use TCP. It's just easier, like a web server thing. But maybe someone doesn't. So then, sorry, can we talk after class? These BitTorrent clients, they also support some UDP protocol. Like you send a packet, and we'll talk about UDP in greater detail later, but basically send a single packet to this IP address. Maybe you get another packet back with some IP address from the swarm. Right. Okay, but so the general idea is we get to multiply the bandwidth available to distribute this file. But there is one problem that has become quite big. I don't know, actually it was always kind of big in the US, and it's spreading over the world. And that is main problem maybe, bandwidth asymmetry. Maybe you've noticed, I don't know if most of you pay for a Comcast or an internet service provider, but you buy this package and they say, 100 megabit down, right? And then in small text it says 2 megabit up, right? So it used to be, at least technology-wise, that there was like limited bandwidth on the link, and you would split it into mostly down, because most people just want to get a bunch of stuff from the internet, and a little bit up so that you can ask for things, or basically acknowledge, okay, I got it, things like that. But you wouldn't really be uploading a lot of contents yourself. This doesn't work so well with peer-to-peer networking, because this sort of offer, you can download 100. You have to have 50 people doing the upload to saturate your downlink, right? And the whole idea here was that we sort of have the number of uploaders grows as the number of users in total. So there's going to be one for every new user that is added to the network. There's only one more user capacity added. Right? So I add 2 megabit up in total to the network, which means basically with BitTorrent all you get is 2 megabit down as well. Right? You have 100 users all providing 2 megabit. The best I can get is 100th of those 200 megabit, so I'm left with 2. You can't go any faster than the uplink speed for this protocol. That's kind of lame. This has nothing to do, the weakness has nothing to do with BitTorrent. This is just how it has to be in a peer-to-peer network. The only source is people behind home links uploading data. So it's always going to kind of stink as long as most people don't have a fast uplink. Yeah?
Theoretically speaking, your download speed, your upload speed should be able to match your download speed, right? Over a physical wire.
Yeah, so that depends on the technology, but at least initially. Now, usually the links are pretty fast, but so it's more of a business-related arrangement. But it used to be that, you could only get so much through this copper wire, say 10 megabit. So now you could choose, like, do you want to go 10 up and 10 down? Or do you want to go 9 9 down and 1 up, because nobody ever uploads anything anyway, so now you go twice as fast almost on the downlink. It's called ADSL, that was the main culprit, and it's still there. It's asymmetric digital subscriber line. That's what you get when you get an internet connection from AT&T. The Comcast or cable sort of networks, I don't think that they had that technical reason for it, but it's still nice for them to not have to deal with so much uplink traffic. Like now most peer-to-peer file sharing just isn't there because it's not that attractive. If you had a gigabit up and a gigabit down, you'd be an extremely good peer-to-peer, yeah. And so you might be using that a lot more. Back in 1996, when I moved to my own apartment in Sweden, I had 100 megabit up and 100 megabit down, and I was paying $30 a month. Things are different in other places. That's gone away too. Now it's usually it's asymmetric links there too. Okay, that's BitTorrent. I think BitTorrent is great. It's really a nice design. It's really good for, oh, I need to distribute these big files to lots of people, especially for nice, legitimate files. And it's out there. It's popular, somewhat popular, but it's been sort of overtaken by or replaced by CDNs, content distribution networks. And we'll have to talk about CDNs another time, but it's a centralized solution. It's not peer-to-peer. Okay, so this is just addressing the bandwidth situation, but there's two more, right? So what if we don't want to have a web server where we go search for files, right? I want to have a nice, fully distributed application where I know, oh, I'm looking for this file. I can go and get it. I can find the peer without having a centralized solution. I can just find who has it in some distributed fashion. So generic search, there's no good solution as far as I know for generic search, sort of Google style, where you just type in some names, some keywords, and you find like you find what you want, like ranked by contents and popularity and all this stuff. The centralized search of a web engine is quite powerful that way. But there's a very elegant solution, or a few very elegant solutions, for something called distributed hash table. So a hash table, you know what that is, lookup table, right? So you have a key. I know the specific file name, let's say, that I want. And now, who's got it? How do we look that up? General idea is you hash the file name, and then using some peer-to-peer magic, which we'll see a couple of variations of, you find a peer that knows where the file is. Right? So we have a distributed hash table. There's two functions. There's put, key and value, and there's get, key. That's it. Okay, so we have a bunch of peers. Okay, let's start with a rendezvous server. It's always like this. To meet some peer. Okay, these are provided. Okay, so I want to join a distributed hash table. I want to do a lookup, or maybe I just want to be part of this big lookup table. Right? This is a little bit like DNS. Although DNS has this nicely structured key, and here we just have a large integer. That's the key. If you have a file name as the key, well, you hash the file name, and then the hash number, the hash value, is the key we're looking for. We should say this is hash. Okay, so I want to join it. I talk to this rendezvous server somehow magically, which we don't need to worry about. It could be a fixed IP address or a website or whatever, a bunch of IP addresses in a text file. Okay, so now the problem is there's like 10 million nodes all wanting to contribute to this network. And I want to somehow ask, like, what is the key? What is the value for this key? And there's 10 million of them. So there's a few different ways we could do it. We could get a list of all 10 million of them, right? And then we send the question to all 10 million of them, and then eventually we get a response. Unfortunately, that means we would have to process requests for 10 million nodes, and we don't want that. So how do we scale it up a little bit better? We need to somehow split all of these keys among lots of different nodes, right? So there's probably more than 10 million nodes. There's probably 100 million or 1 billion keys, right? But they need to be sort of split between these 10 million nodes in some nice fashion so that everyone has the same amount of work to do. And then I need to know which are the nodes that have those keys, right? This seems pretty hard too. And I might be wanting to look up different things every time and so on. So there's a couple of different approaches, but the general idea is called consistent hashing. With consistent hashing, as the size of the hash table changes, the hash buckets of individual items don't really change that much. So maybe you know the normal hash table. We start out with, say, so this is a normal hash table here. We start out with 4 buckets, right? And we add some elements to them, and pretty soon they're almost full, and we decide, okay, we don't want to add a bunch of linked lists to the outside. We don't want to kind of go to the next bucket and so on. There's lots of different ways to implement hash tables, but at some point there's just too much in this table, right? What do? We grow the table. Okay, so maybe now we double the size of the table, right? That's pretty common. So we used to have a bunch of keys and values in here. And now what do we do with this? Like now we have to compute new hash buckets. For every key, we have to recompute which bucket it belongs in. So hopefully, half of them will end up over here. Half of them stay in these buckets, half of them end up over here. That's if we double the size. If we increase the size by some percentage, then everything's going to be just all over the place. Doubling is better. Okay, so this is not consistent hashing. In consistent hashing, we say, oh, it's getting pretty full over here. Oops. It's getting pretty full in these two. Let me put another one in here. Right? And then whatever keys were on this one, we just split those keys and put them here. For the rest, leave them alone. Right? That's essentially consistent hashing. So there's a couple of different ways you can implement consistent hashing in a distributed fashion. And I think the fanciest, most popular one is called chord. I thought we'd take a look at that in a little more detail. Let me see, I have a picture here. Oh, well, this is pretty, but it doesn't say much. Let's take the paper instead. Okay. I think there's okay, here we go. All right. So the hash table, rather than 4 buckets, we say it's a circle. So all the identifiers, say it's a 64-bit identifier, 64-bit key, they all belong to the circle. At the very top is 0, all zeros. You go around, at the very bottom is a 1 and then all zeros, and you go all the way to the top again and it's all ones, right? That's the key circle. And then you want to join this network. You take you pick a random ID. Right? You want to be part of this hash table. You pick a random ID somewhere along the circle. Say here, right? Now you are in charge of the entire key space between whoever has a smaller value than you and you, right? And after you, it's like all of these belong to this guy. I guess, I don't know what this is. All right, so we've split up the key space. That's already pretty good. So now, how do we get to whoever's responsible for the key? Say I'm over here. No, forget where I am. Say I am connected to one of these peers. Right? I just know this guy's IP address. I want to see, oh, what's the value for hash number X? So I ask him, but he's not responsible because X is over here somewhere. So how is he going to find his way to this one who is responsible? Well, one way to do it is that you always just keep track of whoever's after you, right? And whoever's before you on the circle. So if someone wants to, if you want to query this part of the graph, you would go around the circle, contact the next one, and then contact the next one after that. Just ask, who's your successor? Who's your successor? Continue all the way around until you get to here, and you know, oh, that's this guy's responsible. So you ask, what's the value for this key? Okay, so that's the sort of the primitive design. Any comments on that design? What's the worst case number of messages we need in order to make such a query?
Number of nodes.
Number of nodes, exactly. If I'm really unlucky, I start over here, and I really wanted whoever's right behind me, but I only have the next one, so I go forward until I get all the way around, basically. And yeah, okay, but I could have a predecessor too, so then it's only half, right? Still, that's 5 million nodes in our setting, 5 million packets to do one lookup. It's more than that, because it's like connect to this guy, set up a connection, and finally say, hear back that, okay, now ask the next guy. It's really inefficient. Okay, so it's not quite right, but at least we have a nice way to distribute all these keys over a large number of nodes. And when you want to join a network, right, that's also pretty easy. You just pick a random number, you ask any node just to go next, until you find the node who's responsible for your key, for that number that you picked. And then you say, okay, I'm going to join you. And now you have their predecessor pointer. We'll just say, okay, it's him instead. And your next is that one that you just talked to. And we're set. So that's how easily you can join the network. But we have that scalability problem. So how do we make it go faster? Well, the idea, so there's a couple problems. Scalability is the main problem. Then we can talk about robustness later maybe. But basically, how do we get to here more quickly? Yeah.
We can have a bunch of other random nodes in the circle connected.
Okay, I see, yeah. So we could remember some other random nodes in the circle, and because they're all ordered, we can just pick the one that seems the closest. Yeah, that's a good idea. I guess we can do a little bit better than random, at least analytically. From a robustness perspective, maybe random is better. And I don't know, you probably read this paper. I don't know.
No.
Okay, you should read the paper. It's a good paper. Anyway, it's a very famous paper in networking, this one. Okay, so the general idea to make this faster is you keep a bunch of shortcuts. Ideally, you keep a shortcut to halfway across the network, right? So now we've already gone to half. But then you also keep a shortcut to a quarter way, and to an eighth, and to a 16th, right? So you have higher resolution the closer you get to you. So now in one step, we bisect the circle, so we've gone half the way. And because we know that the next guy here has also a pointer to a quarter way, Right? Now we can bisect what's left of this circle in the next step. And the next one has an eighth, so we can bisect again. So in log n number of packets, we can get to any point on the circle. So that's really nice. Now you have a log n number of steps to do a lookup in an arbitrarily large network. Maybe they have some of those pointers in here too. Come on. They don't have a nice picture. Nope. Anyway, this is what it looks like with 1,000 nodes, right? So any one of these nodes you try to join in, they will have a pointer across the whole network, and the next one will have, and there's lots of these like kind of have shortcuts here to go a quarter and so on. And yeah, so that's the quarter circle here, that's the 8th, and here the 16th, right? They get denser and denser. Really nice paper. All right, we are out of time. We do have some more peer-to-peer to discuss, so I guess we'll cover that some more on Wednesday as well. And my office hours are right now.